Hello everyone and welcome back to another episode here of the Hidden Quantum Champions. Today we are looking at Haiqu AI or Haiqu, which is a company in the space of software in the quantum computing stack. And if you are interested in that, if you want to learn how they contribute, and if you want to see the most unique website that I've seen in seeing over 100 companies from the quantum space, then make sure to grab yourself something to drink and stay tuned for today's video as we are exploring Haiqu AI. And with that, let's start right into it. So here is the website. You see it has these three different items here. It says build your advantage, platform, team, open the final frontier, and then inside own the future. Besides that, we have below here start computing. So you can book a demo, join the beta, become a partner and contact. And of course, there's also LinkedIn linked up here. And we see besides the run frontier quantum applications, there is an announcement up here which says Haiqu raised $11 million seed round led by Primary. Let's quickly hop on that and see what this is about. So I'm recording this in February of 2026. And here it says Haiqu keeps the party going. Thank you to our new investors, Primary Venture Partners, Collaborative Found, Alumni Ventures, Qdit Ventures, Silicon Roundabout Ventures, Harlow Capital, and Hyperion Capital. Thank you to our returning investors, Mac Venture Capital and Toyota Ventures, and thank you to our champions across the industry. Now phase 2 begins, our product phase. Don't be a classicist, try our better, read the full press release here. And we are quickly gonna hop into that one before we go back to the website. This is on a different website. So we see here, this is a press release on a press portal. So Haiqu raises $11 million in seed round to enable near-term quantum use cases with new operating system. And here it says, do we have it? Haiqu, an emerging quantum software company, today announced an $11 million seed round led by Primary Ventures with participation of the other ones that we've seen. This fundraise will be used to accelerate the launch of Haiqu's operating system for quantum applications, a hardware-aware quantum software stack for running near-term applications at 100 times less computational cost than existing solutions. So much information in that one sentence. Quickly take a step back. So we are talking about an operating system for a quantum computer. So something that kind of offers you as a user an interface, and then on the other hand handles the hardware part, right? So it sits at the interface between the application layer and the system control in a way. On top of that, it says hardware aware. So this is not, let's say, something that is completely virtualized software layer, but it has some awareness about the underlying quantum hardware, maybe also the classical one. That's what we don't know yet. But that means it understands the capabilities of the hardware. It probably understands the geometry of the chip. If there's, for example, a superconducting chip, not every qubit is connected to each other, right? So there's always an optimization problem of how do I map my algorithm, which is, let's say, a sequence of running different gates on different qubits. How do I map this idea of what I want to actually run onto the existing hardware? Because sometimes I might want to run, I don't know, a Hadamard gate, and then I want to kind of couple two qubits with each other. And these two qubits, like physically on the chip, they are not sitting next to each other. So I need to have an intermediate qubit to somehow do this coupling interaction between the other two, and mapping this, like compiling the idea of the algorithm onto what is actually possible on the chip, requires to have some awareness of the hardware. So you need to understand which qubits are sitting where, which operations I have available. Maybe I cannot run every single gate on every single qubit. And that, I think, is what this hardware awareness is required for. And then it says 100 times less computational cost. So that means you have probably less deeper circuits. And that is important because as we are talking about these concepts of, for example, error correction of qubits, you need more and more qubits to actually run something. And that means it becomes more and more hard to actually reach the goal until which a quantum computer becomes efficient for your problem or for solving problems. And that's why like these efficiency boosts here, they are required. And I guess here part of that is because of this hardware awareness that they integrated. Let's not go through the whole article in details for the sake of the video, but I mean, very interesting to read through it. Something that is, for example, notably interesting, I think, is following work in anomaly detection that was affirmed by IBM and Bank of Montreal. Haiqu will leverage the funding to continue validating near-term quantum use cases in industries like finance, healthcare, aviation, life science, and more. I think that is very interesting to see that this is like super focused on applications. So where can actually quantum bring a new perspective into existing industries? I don't want to talk about quantum advantage at this point because it's a quite difficult term and quite often discussed. There's also some note here on machine learning, computational fluid dynamics. We've seen these topics popping up with multiple companies in the list, in the hidden champions. So these are indeed typical areas where people are actually thinking about applying quantum computers. So let's hop back on the starting page. We can see that we have these three different areas here. As per usual, we talk about the people in the company as the great final of the series of the episode. But now let's quickly explore, this time from the right side. So own the future. So we see there are some case studies here as well. We can quickly hop into those. Let's quickly see what this is about. We've heard about it before. So there's like Capgemini, GSK, and IBM. So enabling quantum chemistry for drug discovery with Haiqu. The pharmaceutical industry seeks drugs with high potency and precise selectivity to improve efficiency, reduce side effects, and lower late-stage failure rates. Targeted covalent drugs are especially promising because they form a specific irreversible bond with a target protein by a reactive chemical group called a warhead. When properly tuned, this mechanism delivers exceptional potency and durability, aspirin being one of the earliest examples. The challenge is predicting warhead reactivity. Higher reactivity generally improves potency, but excessive reactivity undermines selectivity. Accurately balancing this trade-off remains a major bottleneck in drug discovery. With R&D costs exceeding $2 billion per drug, pharma increasingly combines machine learning and computational chemistry to accelerate discovery. A powerful approach uses first principles calculations to generate quantum fingerprints, in quotation marks, physically grounded features that improve reactivity prediction. However, classical simulation methods scale poorly. They rely on approximations that are either too inaccurate to capture critical many-body effects or too expensive for practical screening. So that's the problem, right? Quantum chemistry workloads exceed today's hardware limits in circuit depth, noise, and cost. Quantum computing offers a solution, but until now has been constrained by hardware noise, limiting usable circuit depth to a few hundred 2-qubit gates. So circuit depth refers to, in this case, as in how many gates you apply after another in order to kind of create your algorithm. So if you want to, for example, couple 2 qubits, then you would use one gate for that. That would be a circuit depth of 1, and then as you go along, it gets deeper and deeper. The more qubits you have, the more things you can run in parallel, but sometimes you still require a certain circuit depth. This is this optimization problem of, let's say, compiling the algorithm that you actually want onto the hardware that I was talking about before, right? So Haiqu, working with Capgemini, IBM, and GSK, broke this barrier by demonstrating one of the largest electronic structure Hamiltonian simulations ever run on real quantum hardware for covalent drug warheads. Using advanced circuit compression and middleware execution, the team initially reduced circuit depth by 15.5 times and further allowed end-to-end execution by running subcircuits up to 371 gates. So solution decomposed prohibitive quantum runs in hardware-friendly separable blocks. So collectively, these results established a scalable hardware-realistic path for running Hamiltonian simulations on large active spaces while maintaining sufficient accuracy for molecular reactivity prediction. And here we see then how the circuit depth was going down. So if you just start with a naive approach, you might have, 10,000, I think, and then it's far from what is actually achievable today. Think about the machines, the superconducting qubit machines with maybe 100 of qubits, or maybe more than 100, but let's say roughly 100. So in order to have 10,000, you would still need more than 100 gates to run, to have 1,000 operations, but this is circuit depth, so you would need to have 10,000 of operations to run on those to have a circuit depth of 10,000, and that is not achievable because there's just too much noise in this near intermediate state quantum computers, so NISQ quantum computers, right? And now the idea is that, okay, you can, I think as I understand here, you have these blocks, I don't remember here, separable blocks. So you probably chop up your algorithm into those blocks. You can run those blocks with the hardware that you have, and then you combine everything into a final solution. That's would be my guess on how that works. So let's see. Here it says Haiqu decompose quantum circuits into hardware-friendly blocks, enabling quantum chemistry workloads. Left panel, execution with Haiqu middleware, blue squares, lower right panel. Retain coherent signals and closely track ideal trajectories, green crosses. While runs using Qiskit's built-in error mitigation, orange squares, collapse toward a noise-dominated baseline, black dashed line. And that's referring to this little plot here. I quickly zoom in. So here you see that you have the ideal simulator as in this gray line here. You have the black dashed line, which I think was also explained here, is the noise dominated baseline. So basically you don't see anything. That's what the default QPU state does. It goes up here. And then with the Haiqu different versions, so the default, the Haiqu QPU and the fake Torino simulator, I guess, you can see that it kind of tracks, or at least is much closer to this gray line here, to the optimal line, than the orange dots that you see up here when you just use the normal error mitigation that comes with the hardware. So for decision makers, the implications are clear and immediate. Haiqu dramatically lowers the cost and increases the performance of quantum chemistry workloads, transforming quantum computing from a long-term theoretical research bet into a near-term commercial piloting program on real quantum hardware. By making deep Hamiltonian simulations feasible on today's quantum hardware, Haiqu enables pharmaceutical teams to, first of all, explore large and more realistic molecule spaces. Second, generate predictive quantum features unavailable to classical methods. Third, integrate quantum simulations directly into machine learning-driven discovery pipelines. And fourth, accelerate early-stage drug discovery while reducing computational cost and increasing the success of the pilot experiments. Crucially, it is not a promise for the next decade. Haiqu makes high-value quantum workloads commercially viable today, allowing enterprises to capture competitive advantage years ahead of hardware-only roadmaps. So that is what this is about, and there's also a full research paper linked down there. There's also something with HSBC, which will then go into the financial We have seen already other companies as well talking about financially related stuff like portfolio optimization. Here it says loading financial data at new scale, enabling realistic quantum Monte Carlo for finance. Monte Carlo is random or randomization based simulation method for complex systems. I guess this will also go more into the details here of how that works. So quantitative finance is fundamentally about allocating capital and redistributing risk in ways that support long-term economic health. So I guess that also goes in the direction of portfolio optimization. Listening to that first sentence, by making uncertainty explicit and actionable, quantitative methods help firms allocate resources with confidence and contribute to more transparent, reliable markets. And then there is some explanation similar to the other one that we've seen before about how this is actually being implemented. There's another one here with Airbus and BMW, so executing record-scale quantum computational fluid dynamics on today's hardware. People want safe, affordable, and comfortable transportation. The economics of delivering quality to end customers are set early in the value chain. Aircraft manufacturers make efficient decisions that airlines convert into lower operation costs, with people then experience lower fares and improve comfort. The introduction of Airbus A320 as sharklets to reduce wing tip vortex drag and cut fuel burn is a good example. Airlines recovered retrofit costs in a little as 2 years per aircraft, achieved fleet-wide savings in the multi-billion dollar, and supported lower operating costs as per seat. And then there's also some fluid dynamic, quantum computational fluid dynamics happening here. To do this, I think what I see here looks like a little bit of a optimization, possibly in similar to a variational eigensolver or something like that, because it looks like there's some closed loop operation happening here, but I'm not going to go into the details now. So if you're interested in that, as always, let me know down in the comments below. Then we can also hop into one of these case studies, hop into one of the research papers behind it. But as always, we do that upon your request, your interest on that, right? So folding mRNA on 120 qubits. So that's the third one, the fourth one that we see here. So biology is governed by the relationship between molecular form and biological function. Cellular processes such as signaling, metabolism, and regulation depend on proteins that are precisely folded to perform specific tasks. Fundamentally, protein folding is an optimization problem with exponential complexity, making accurate physics-based simulations impractical at scale on classical computers. As proteins grow larger, computational cost rises rapidly, limiting the use of traditional methods in drug discovery and molecular design. Quantum computing offers a new approach by mapping protein folding to a problem that quantum algorithms are naturally suited to solve. Techniques such as variational quantum algorithms can directly search for low-energy configurations, the biologically relevant folded states, within vast and complex solution spaces. That's again something that quantum computers naturally are good for. It is physics, or the mechanisms are governed by quantum physics. The quantum computer uses quantum physics for its computation, so it makes sense to kind of use this platform to solve these types of problems, like protein folding in this case. And this is done with this variational quantum algorithm approach, which we've also talked about previously in other episodes. Okay, and then we come here to the news section that we've seen, and there's also a blog space and white papers available here as well. For example, on this quantum embeddings for anomaly detection. I'm not going to go into the details of this for the sake of time, but I think it is very interesting to kind of read into those, because that's probably where, let's say, the I don't want to call it secret sauce, but like, because it's open, right? But where the core of this idea of this company lies is in translating those ideas into business value. I don't know if you want to call it like this, but like using the understanding on the one side of the quantum system, on the other side of the problems, and then kind of merging that into full solutions here. Let's quickly go back and also check out the platform part. So build your advantage. I'm to quantum program today already. So overview, quantum software for winners. That's the 100 times improvement. So run algorithms with 100 times more operations, get results in seconds, not weeks, and use 1000 times less quantum cloud time, which also means 1000 times less cost for quantum cloud, right? So that's interesting for companies when thinking about using quantum computers for new developments. So build your advantage on Haiqu, years ahead of competitors. And then we see here some nice animations. You can see that basically it runs on various different systems. So we see spin, trapped ions, and so on. This is all part of this secure cloud, available 99.98% of the time. And here it says total 27 jobs, 1 running, 26 finished, and so on. That's just an example, I guess. Or maybe that is the company stats. I don't know. Could also be, right, that they have finished 26 jobs already and that one is running now. Okay. Don't want to hypothesize too much here. And then from Haiqu SDK, import Haiqu. That's an example of what the code would look like. So design, run, and manage. In the design part, it says build industry first applications easily. Our SDK, so software development kit, and development environment contain all the tools you need to systematically build applications and new IP. Then on the run part, make optimal execution the default on any hardware. So run hybrid applications at leading performance and cost efficiency. And then finally on the manage side, get full visibility into every quantum job. Track your jobs with experiment management, circuit versioning, and analytics that help you scale. Manage your IP in full security. IP is an important topic. I've mentioned that also in a previous episode. A lot of startups are out there right now, and building your IP stack, making sure that your IP is secured so that as a company you have some differentiator from others that is secured, is an important part. And that's why this secure cloud is of course also very important, because you want to make sure that your IP remains protected so that you can get as a company this competitive advantage based on using quantum technology. So then we have speedrun your applications on superior quantum middleware, and that's where they are, right? They are on the quantum middleware side of things. So user environment, secure cloud, and quantum HPC. The Haiqu SDK, so build state-of-the-art applications out of the box. Use tools like circuit optimization, lightweight error mitigation, data loading, and more. Then the runtime part says runtime is where the magic happens. Our middleware delivers up to 100 times more algorithmic operations. Our orchestration infrastructure cuts execution time and costs by up to 1000 times. And then on the other side, you have the HPC. So that's the hardware side. So run hardware where workflows on any QPU modality in a fully secure cloud environment. So that's basically the whole integrations stack. So at the very hardware side, you have the QPU, so the chip with your qubits on it, combined with the HPC, so the high performance computer, so that you can run these variational loops where you kind of use a classical computer to optimize the operation on the QPU. So kind of machine learning, optimizing the parameters on the quantum machine to solve a specific algorithm for you. Then you have the control and error correction part, which sits on top or besides this. So error correction is something that is coming more and more into reality, right? And then you have the runtime part. You see here orchestration, hardware characterization, middleware, and the algorithms and subroutines. So orchestration as in, I think I don't need to explain those in detail now. And then, of course, on top of that, you have your application, so your translation of industry knowledge into an algorithm that is then basically broken down within this runtime into some operations that will later on be executed on this hardware. I also love these nice animations here, or these images. I think they are making it very clear, and they also look very unique, right? There's another animation coming in here. So start on the performance frontier, no more toy problems. Data loading, middleware, and then runtime infrastructure again. So load real data sets for the first time, encode unstructured data with thousands of features, structured data with millions of features. So that is definitely one topic. If I have, I don't know, 80 qubits, how do I actually encode all of my information? Because the most, let's say, a naive approach would be, okay, 1 qubit can encode 1 bit of information, so it can either be 1 or 0. If you do that, then you can basically only have a maximum of 80 bit, if you have 80 qubits, 80 bit of information, which is probably not what you want. So you want to use things like angular encoding, where you kind of flip the qubit into a specific angle, into a specific position, depending on the information that you put in there. But there are also other ways of encoding information. And this is something that is very important, because it at the end limits the size of the problem that you can try to have the quantum computer solve for you. So loading data and creating those, getting those big data sets into the quantum computer is one part. Then middleware, of course, we've talked about that before, like getting stuff efficiently executed on a quantum computer, right? So combined circuit optimization and lightning fast error mitigation to run applications with 100 times more algorithmic operations. And then finally, the runtime infrastructure, so run complex application pipelines up to 1,000 times more cost efficient, or don't be lazy and run 1,000 times more at the same price, right? So, and then here we see again the use cases that are being targeted. So deploy novel applications that run change industries. So we see some nice pictures characterizing the different industries. Here, for example, we see an automotive, a car, there's a jet, there's a turbine, and many others. It says life science, finance, automotive, aerospace, energy, and logistics. In the life science, we see the protein dynamics and drug interactions and the genomic patterns. So that is related to what we've seen before. On the finance side, we see the anomaly detection, systemic risk modeling, and derivatives pricing. On the automotive side, we see fluid dynamic simulation. That's also something we've heard before. Manufacturing optimization, and then battery and catalyst chemistry. In the aerospace, we see hypersonic flow modeling. That's also related to the fluid dynamics we've seen before, I would assume. Composite materials, and then mission optimization. In energy, we see grid optimization, which is again an optimization problem, right? Subsurface analysis, and then methane emission. And then in the logistics space, we see adaptive routing, demand prediction, and inventory optimization. And then we are already here at the final part. So Haiqu's technology allowed for the execution of circuits that would otherwise be impossible to run, and so on. So these are basically just testimonials in a loop, in a carousel running through here. Now let's quickly also check out the team behind the company as per usual. Let's quickly go here and talk about the vision first. So opening the final frontier of computing. Nature has been quantum computing for 13.8 billion years. That is relating to the idea that the universe is operating on quantum theory, right? Which might be a correct hypothesis, might be not. So far, quantum is the most precise theory of nature that we ever had by any measurement. In every photosynthesis, every protein fold, every entangled particle, once people start quantum computing, a new abundance of knowledge will lift industries and civilization. At Haiqu, we are designing the software that lets anyone master this universal force to simulate physics in full model markets before they move and design a world in balance. We are the tool makers for a new creative frontier. You are the explorers. Progress walks on 2 feet, theory and experiment. So put down the toy problems and get empirical. Start running. Nice simulation of a tree relating to the photosynthesis. There's some statistics about the team. So you see here the team growing over time, divided into PhDs, postdocs, and everyone else. And then here we see the founders. So Mikola is the CTO and co-founder. He also has, I think, some background in quantum. So he mastered quantum-inspired numerics to study exotic physics, materials networks, AI. Quantum computing was cool. So before quantum computing was cool. He grew and led SoftServe Inc., global deep tech R&D team of 100 plus experts, serving as frontier lab for Fortune 100 companies, and now is working at Haiqu, before at the Weizmann Institute of Science, which is very well renovated, and also the Max Planck Institute. And then we have Richard as the co-founder and CEO of the company, while most people at Haiqu obsess over really small things like qubits. Richard obsesses over really big things like company vision and elephants and how computing can save them. With a Stanford degree in engineering physics and entrepreneurial experience at the intersection of satellites and mobility, he founded Haiqu because waiting 15 years for quantum advantage was unacceptable. So that's kind of the idea. And then here we see the whole team. By the way, I really like those animation. Reminds me a little bit of Harry Potter, of these newspaper articles where you see that like the people are somehow moving in the newspapers and on the photos, right? And then here we see the team of people. We see that they have all various types of backgrounds in the area of compute, of research. So we see, for example, here again Weizmann, ETH in Zurich. So I'm sitting in Switzerland, not too far from ETH, University of Chicago, Illinois, Ottawa. So various different spots, also various different countries. Aachen University, that's actually where I studied physics. So various different backgrounds and various different places. You also see Paris here. And then there's a list of the investors and also institutions that are collaborating with Haiqu. And there's, of course, also again ETH Zurich in here, Stanford University, Max Planck Institute, University of Chicago, University of Zurich, and many others. There's also this global footprint, I guess, type of setup. I actually had to search a little bit to find where I would be on that map. I leave that one up to you, so pause the screen and look for it. But I really like the idea. And then again, here we see the I think like case study related things. So it says media here. And then of course the call to action. Now we could also go here and say start computing and book a demo or become a partner. But I will leave this one up to you because I'm already almost up to the next company. So if you don't want to miss out about that one, make sure to subscribe to this channel. If you want to see any other series, any other episode of this series, check out the Hidden Quantum Champions playlist on this YouTube channel. With that, as always, stay hydrated and see you in the next one. Bye-bye.